So how the address of underscore underscore kernel underscore v call is determined. So we know user processes on 32-bit systems, they need underscore underscore kernel underscore v call to execute system calls. But this address of this underscore underscore kernel v call, it is not fixed. So kernel actually, it passes the address of this particular kernel underscore v call using at underscore sysinfo elf parameter. So it uses this at underscore sysinfo elf parameter to pass the address of underscore underscore kernel underscore v call to user land processes. So it uses something known as ELF auxiliary vectors. This is an ELF auxiliary vectors. So ELF auxiliary vectors are a mechanism to transfer certain kernel level information to the user processes. Example of such information is at underscore sysinfo, which actually contains the address of underscore underscore kernel underscore v call. So auxiliary vectors are a list of key value pairs that the kernel's ELF binary loader, so kernel has an ELF binary loader, which is present in this particular location in the kernel source, passes it. So it is a list of kernel key value pairs that the kernel ELF binary loader constructs when a new executable image is loaded into a process. So whenever a new image or new process starts, the kernel's ELF binary loader will construct a list of key value pairs, which are nothing but ELF auxiliary vectors. So ELF loader, it passes the ELF file, it maps the various program segments in the memory, it sets up the entry point, it initializes the process tag, and it puts the ELF auxiliary vectors on the process tag, along with the other information like argc, argv, and envp. So ELF loader puts an array of ELF auxiliary vectors at the bottom of the process stack. So how can I observe these ELF auxiliary vectors? So there are few methods for searching ELF auxiliary vectors. The first method is there's a function known as library call get aux val. So aux is nothing but auxiliary vectors. So if you want to get the address of underscore underscore kernel underscore v call, you can call get aux val with at underscore sysinfo argument. Or as it is placing it at the end of the process tag, you can iterate to the end of the environmental variables and you can pass the ELF auxiliary vectors from there. From the shell, you can also verify, you can also observe the auxiliary vectors which was supplied to an executable by setting ld underscore show underscore auxv environmental variable while you are launching the application. If you set this particular variable to 1 while you are launching the process, you can see the auxiliary vectors which were passed. So let's do it. So let's, for the ls, let's see the auxiliary vectors. So it is, you can see here, it is actually showing the auxiliary vectors. You can see it also has different auxiliary vectors. It does not have at underscore sysinfo because this is an x64 application. At underscore sysinfo auxiliary vector is present only on 32-bit application. Sysenter and sysexit are used, instructions they are used on 32-bit processor. But we have different auxiliary vectors which are being passed by the kernel to user space. Space size, UID, effective UID, group ID, effective group ID, and different other platforms is being used. So the different information is being shared by the kernel to the user space through auxiliary vectors. So this is the first mechanism by which you can verify the auxiliary vectors. The second mechanism is you actually use get aux val and then you read all the auxiliary vectors. So let's see that example here. So I'm calling get aux val and you need to include this particular header file which has the definitions of this. So the same thing which ld underscore aux, the environmental variable is being shown. We are doing it from a user app. So get AUX val will actually give the value of a particular AUX auxiliary vector. So we are also interested in AT underscore sysinfo because this actually contains the address of underscore underscore kernel underscore vsyscall. So let's load this. Let's first compile this for 32-bit. And now you can see here AT underscore sysinfo is here. It contains the system call. V kernel underscore vsyscall address. But if I compile this for normal x64, that is 0. So it is only AT underscore sysinfo auxiliary vector is only being updated by the kernel when we are using x86 platform. So now let's actually use and let's call underscore underscore kernel underscore vsyscall from our user space process, which will internally call sysenter. Okay, let's do that. So sysinfo, we need to get the address of underscore underscore kernel underscore vsyscall, which will be getting through get AUX val. So we got the address. Then let's get the system call, fill the system call number, and this is the same lines in the previous example. Now let's use an inline assembly and let's actually go to this particular location. So we fill the system call number first. We fill the parameter and then we call this particular location which we are specifying here. So system call number is %L0, exit status is %L1, sysinfo is %L2, and then we are also specifying the global register. So this is not needed. So let's run this program, compile it for 32-bit. Let's check the output of it. And this is how you executed user program using sysenter. So this is the fastest system call using int0x80 slow because it uses interrupt. So they provided instructions, processor provided instructions like sysenter and sysexit, which is used for this. So switching to kernel mode in the optimized manner. So let's also try accessing some other system calls. Let's now access write system calls. So I want to actually write hello world on the console. How can I do it? How can I write hello world on the console? So hello world system call number. Let's verify the hello world system call number. So system call table, open the system call table of x86. The write system call, it has a system call number 4. So let's update the system call number 4. And we know the write system call, it accepts 3 arguments. One is a file descriptor, second one is a file descriptor, second one is the buffer which it wants to write, the third one is the size of the buffer. So now let's have those. This is the buffer I want to write, this is the buffer length. So first I fill the system call number into EAX. Then the first argument is the file descriptor. I'm filling it I. I is immediate operand. So 1 is the file descriptor of standard output. So I'm writing it into EBX. And I'm writing the contents of the buffer into ECX, length into EDX, and then I'm calling the address of underscore underscore kernel vsyscall. This will jump to there, which actually calls sysenter. So I am also mentioning the remaining registers which have been used here into global list. Let's compile this. So this is how we can execute a system call using sysenter. So we have executed different system calls. We have tried executing exit system call from using sysenter, which means we are actually calling underscore underscore kernel vsyscall. Then we have also executed write system call using our assembly inline assembly code. This is all about this. Till now we have seen only 32-bit system calls. Now let's look into 64-bit fast system calls. So the instructions for switching from current privilege level 3 to current privilege level 0 on 64-bit is syscall. And the instruction is sysret. So switching from user mode to kernel mode, CPL3 to CPL0 is syscall. Kernel mode to user mode is sysret. So again from Intel manual, it says syscall invokes an OS system call handler at privileged level 0. How does this it performs? It does by loading instruction pointer from this particular MSR. So this particular MSR needs to have the address of the function which it needs to execute. So it copies the value of the address which is present in this particular MSR into instruction pointer, and this is how the instruction, that particular function gets executed. So in other words, if kernel needs to receive incoming system calls, it must register the address of the code that will execute when a system call occurs by writing its address to this particular MSR. So it also does it here in this particular file. There's a function known as syscall in it. So you have syscall in it here. This is where it actually updates the register. MSR underscore L star with the function which it needs to execute. So let's go into this function, entry underscore system call 64. And this function is present in our assembly. It's written in assembly. This is the file where this particular function is present. So you can see here it says this is the only entry point used for 64-bit system calls. So, and it mentions the system call number is present here. The return address is stored in different register. This is an important point here. So this function actually, after performing all those steps, saving registers and all, it actually calls do underscore syscall 64. This function finally calls syscall table. Which actually calls that particular system call number. And so whatever you have registered, it will be called. Very simple. You have to register that particular address in the MSR and that particular function will be called. So let's dump the call trace. What happens when hello init is being called? We know the test underscore hello init or the module init function is being executed in process space. The system call is being used whenever the INS mode is being called. Internally, a system call is being used to switch to kernel space. So actually, let's see the first function which is of the kernel space here. The first function you can see here is entry underscore syscall 64. This is what we have seen. And it actually calls do underscore syscall underscore 64. This is also which we have seen here. Do underscore syscall underscore 64. Then it actually goes and it calls that particular actual system call depending on the system call number. It also prints the values of RAX, RBX, and all those registers. So now let's perform the same operation using inline assembly. Now let's actually call syscall instruction using inline assembly. So system call number for exit is 60. Now change the exit status. Let's change the exit status to 12. So first fill the system call number in RAX register. And then the first parameter in RDA register, call the instructions is call. This is the input para operates global first. So now we have compiled this for 64-bit. So this is how we got the 12, the return value 12, which we have called exit of 12. So we got 12. So these are the various mechanisms by which we can call system calls. We have seen int $x80, then we have seen sys enter, then we have seen syscall. So how a system call is executed in other architectures. So you can find this information from man page. Man to syscall will tell you how the other architectures are calling system call. So man to syscall, you can see this is the man page. Come down, you can see the various mechanisms of instructions which are being used to call syscall, and the register which are being used for storing the syscall number and the return value. On i386, the old architecture, it uses int 0x80 and uses EAX for system call number and EAX for the return value. If you come down, now currently both are x86_64 and x32 they are using syscall. ARM it uses SWI and 64-bit ARM it uses SVC. So each and every architecture they have an instruction or they have a mechanism to switch from user mode to kernel mode. Return value of system calls. So all system calls they return long. So positive value or 0 value denotes successful termination of the system call. Negative value denotes an error. The value of this error, the negative value is negated and it's stored in the error number variable. So whatever the value you get negative value, it is converted to positive and updated into the error number variable. And this error number variable is not set or used by the Linux kernel. The wrapper routines which handle the task of setting this variable handles the task of setting this variable. So the wrapper routines, glibc wrapper routines, after return from system call, if it finds that there is a error, system call did not perform successfully, termination of system call was failed, or there was some problem in executing the system call, then it updates the error number variable by taking the negation of the return value of system call. Let's do that. Let's actually call DUP. DUP is the system call number is 41. I'm using again, say, I'm calling it through underscore kernel basis call. So what I'm doing is DUP it accepts like DUP system call. It accepts an old file descriptor and duplicates a file descriptor. But the return value is when you pass a wrong value, it says it's not an open file descriptor, bad file descriptor. So what I will do is I'll pass some file descriptor, I give a wrong file descriptor. And I actually call system call. So this is how I call the system call. And I store the return value here. And I print the value of ernum. And I print the value of return value. So let's see what happens. Do you think ernum will be updated or not? Let's see. So let's compare the user program. Let's run it. You can see ernum is 0 because it is not being updated by Linux kernel. The return value of the system call is -9. So let's see what is the actual meaning of 9. 9 is EBAT file descriptor, which is what we are doing. We are actually trying to check whether it returns EBAT file descriptor. The return value is 9 and num is 0. So when you call kernel does not update, this means kernel does not update the num. So C library provides a small function syscall, which actually invokes the system call. So this is actually provided to use when you are invoking a system call that has no wrapper function in the C library. So what syscall does, it saves the CPU registers before making the system call. It restores the registers upon returning from the system call, and it stores any error code returned by the system call in num if an error occurs. So this is all performed by syscall. So whenever you call syscall, it saves the CPU registers before calling the system call, making a system call. It restores the CPU registers after the system call, and it also stores an error code written by the system call in num. So you have to include the header file. Then you have the function syscall. The first argument is the number, system call number, and the remaining arguments are the parameters which you want to pass. So now let's actually call DUB using this. So system call, so sysinfo is not needed now. So we have system call number, which is the first parameter. Next parameter is old file descriptor. The return value I'm storing here, and then I'm printing the num and the return value. So now you can see here, the return value is -1 and the num is 9. So you can see the difference here. In the previous example and this example here, we directly call system call from our application. The kernel has written -9 and there is no updation of num because we are not updating. But when we have used a wrapper, the return value is changed and num is updated. So this is the definition of glibc. So this is where syscall is actually present. Let's look into syscall. So you can see this is how syscall is defined. It's an assembly. It fills the registers. System call. It then compares it, check if there is any error. Then it updates the error handler. Finally, it returns it. So this is the how you call syscall. This particular function will execute. It fills the system call number, saves the registers before calling. It actually saves it before calling, and then it updates the parameters with the parameters. It calls syscall. So what happens if I pass a system call number which is not implemented? So I know syscall, it accepts a system call number. What happens if I pass a system call number which is not implemented? Non-implemented system calls are written no sys. So let's actually try that. So I pass something known as 941, which is not actually implemented, and I actually execute syscall. So let's check the return value now. What happens to the return value? So let's actually compile it. So you can see the return value is -1 and num is updated for 38. So let's see what is num of 38. It is no sys, which means function is not implemented. So non-implemented system calls, they actually return no sys. Let's complete our session by completing this VDSO topic, the final topic, VDSO. VDSO stands for Virtual Dynamic Shared Object, which we have already seen the NX7 VDSO. Kernel automatically maps a shared library into the address space of all user space applications. So VDSO is a small shared library which the kernel automatically maps into the address space of all user space application. So communication, we know already, communication between user space and kernel happens through system calls. Example of system calls are fork, pfork, etc. And we have already seen what happens when a system call is being invoked by a process. Process executes a special instruction. It saves the content of registers. Execution of kernel function happens. When the system call is returned, depending on whether you're using 0x8, 0 and all, the registers are saved. And finally, execution is resumed. So this we have already seen. We have seen sys exit, sys enter, sys call, sys read, etc. But numerous clock cycles are spent just to make this special kind of function calls. What are the problems you see in this mechanism? So you have to call sys enter, you have to call sys exit, you have to save the registers and all. What problems do you see in this mechanism? There are numerous clock cycles spent. There are some system calls which the kernel provides, which user space code ends up using frequently. So to the point that such calls actually dominate overall performance. Example of such calls are get time of day. Because performance is now reduced because the frequency of call and then the context switch happens of entering and exiting the system call. Get time of day, and there are some other functions which do not actually write any data. They only read the data. They return a value which is stored in the kernel. For example, get time of day, it returns the time of the day. They're actually safe. I do not need to perform any context switch if I want to actually read the time. So with VDSO, what kernel does is, kernel actually arranges the required information to be placed in memory the process can access. So instead of happening a switch, context switch from user mode to kernel mode, kernel actually places this particular information in the memory of the process. So my process can actually access it without context switch. So let's see an example here. I'm calling get time of day function, and I'm reading the time of the day. So I'm actually, this example will tell you like the speed. I want to calculate the speed it takes to calculate get time of day through the wrapper function provided by glibs. So let's run this. So I have to call through loop count. So let's say I said 1,000 times or 10,000 times. So you can see how easily it is completed, taking very less time to 20 seconds to call for executing get time of day this many times. Not only 20, it's not 20 seconds actually. It's 2 millis, 0 to 02, right? It's not 20 seconds at all. It's in milliseconds, 20 milliseconds. Not even 20, it's 20 milliseconds. It is taking 20 milliseconds to execute get time of day this many number of times. Now let's do it through our own wrapper function instead of going through user space. So let's actually call syscall. Instead of wrapper function, let's directly use syscall, which actually calls system call, syscall instruction. So syscall, the system call number, which is present here in unihistory.h, and the arguments. Execute this program. Now run this. So let's say the same number. So you can see it takes 44 milliseconds to execute the same amount of call which is being executed here. So it's very less. You can see compared to VDSO, which the wrapper function is calling through VDSO, and through system call, the amount is very less. So with VDSO, the kernel maps some information about system calls, the read-only information into the process space, and performance is increased. So when you're tracing system calls with strace, system calls which are exported by VDSO will not appear in the trace output. But you can capture those system calls using ltrace instead of strace. So let's see, I'm using this particular example. This is actually internally using VDSO. Let's say strace now. You can see here, sorry, strace of 1. You can see here there's nowhere mention of get time of day. Get time of day is not mentioned here because it is being mapped to process address space. Now I actually use ltrace, and now you can see get time of day is being used. So as it is not switching, this is it's not actually calling system call. Strace will not actually switch. So when you say LDD, it actually shows you the VDSO. This is the shared library which is mapped by kernel. But when you search it in file system, you will not find any results regarding this. You will not find any location of this particular thing. So why we do not have this on the file system? Because it is a virtual shared object. It does not have any physical file on the disk. It's a part of the kernel which is exported into every program's address space when it is loaded. Then we have something known as VSys calls. So VSys calls are virtual system calls. This was the oldest mechanism in the Linux kernel, which was designed to accelerate execution of certain system calls. This is a file where VSys calls are implemented in kernel, and only 3 system calls are being supported in case of VSys calls. Linux kernel maps into user space a page which contains some variables and implementation of some system calls. So you can verify it by here. But this is an older mechanism, only has space for 4 system calls. And there is some security issues here. So if you call cat proc self maps, you can verify it. There's something known as VSys call. And then you have VDSO. Verify the address here. This is the address now. This is the address for VSys call. Now you can see here, address is changed. But address is not changed for VSys call. Address is same. So VSys call, there is no address space layout randomization. It remains at the same location, whereas the location of VDSO area is randomized. So that's the reason VDSO is used. This offers improved safety through memory space randomization, and it supports more than 4 system calls. Ellipse internally uses VDSO. If the kernel does not have support for VDSO, like older kernels which do not have support for VDSO, Ellipse will make a traditional syscall.